This video explains concentric loaded grade 300 compression member is restrained such that its effective length for buckling are LEX 6 meters and LEY 3 meters if the service dead load, permanent and live imposed axial loads are 500 kN and 300 kN respectively, determining an efficient universal beam sections. Now to obtain a trial columns, we assume the alpha C value 0.7. Now that alpha C value is the given in the standard. Alpha C value is the member slenderness reduction factor alpha C that we assume 0.7. So now design load is 1.2 times dead load plus 1. Design load is 1.2 times dead load plus 1.5 times live load. So 1.2 times the dead load is 500 kilonewton, that is given in the questions, 500 kilonewtons, and the live load is given 300 kilonewtons, and that is given 1050 kilonewton. Now these equations taken from AS 1170.0, and that is on the on AS 117.0 on page number 15. On clause 4.2 point strength, we have 1.2 G plus 1.5 Q. Now design strength is equal to 5 times the member capacity equal to 5 times alpha C NS. Now that member capacity is given on page number 83, where you have NC is equal to alpha C NS, and that is alpha C NS for NC, and NS is this NS value is a section capacity. That section capacity is here, that is given again in the standard, where on page number 81 on clause 6.2.1 we have NS, KF, AN, FY. We substitute the value. N star is 1050 times 1000 to convert into Newton, times 0.9. Alpha C we assume 0.7. KF is 1, we take the KF equal to 1, just assume. Gross area we need to calculate. FY value is 5550 millimeter square. So that's the gross area we calculated. Based on that gross area, we can try the universal beam from this gross area which we calculated 55555, which has a 360 UB 44.7. So we need to calculate the gross area which is more than that is more than this 5555. So we found that 5720 gross area, that is 360 UB 44.7, that we can try. So gross area 5720 millimeter square for 360 UB 44.7. Now KF value is given for this one, so 360 UB 44.7, and the KF value is given 0.930, that is on page number 15. RX and RY, radius of gyration for 360 UB 44.7. RX value is 146 millimeter and RY is 37.6 millimeter. Now based on that, we can find modify compression member slenderness lambda NX. That equation is given in the standard on page number 84, that lambda N value. We can substitute the effective length 6000 millimeters, that is given in the questions, 6000 millimeters LEX over RX, that we just recorded 146, times the form factors we found from one steel table 0.930, times the yield strength is 320, that is coming from one steel table. For 360 UB 44.7, we can find 360, we can find 320 yield strengths, that is given in the one steel tables. 320 over 250, so that is 45. Lambda NY respectively, we just need to take the LE and RY different value because that is given in the questions. LEY is 3000 millimeters and RY we found 37.6, give us 87. Now member section constant alpha b equal to 0 from table 6.3.32. On page number 85, we have two tables, one for kf equal to 1, another one is kf less than 1. In our case kf is less than 1, so in that case we can use table 6.3.32. In that case compressor member section constant alpha b is 0 because hot roll universal beam, so alpha b equal to 0. Now alpha c requires some calculations. So first of all we need to get the lambda n, which is the modified compression member slenderness. We need to get the maximum between these 45 and 87, that is lambda nx and lambda ny. So maximum value is 87, so that is lambda n. Once we get this lambda n, we need to use the table 6.3.3 on 3 on page number 86. Table 6.3.3 member slenderness reduction factor alpha c is given. Now we have various values given, but we need to find it lambda n for 87, so I'm going to use 85, and for alpha b is 0.645. 87 we need to find, let's put x, and for 90 is 0.610, so that is taken from this table. Now the interpolations, 90 take away 85 respectively 0.610, take away 0.65, 87 take away 85, x take away 0.645. the calculations gives x value, which is alpha c value is 0.631. Now nominal section moment capacity ns, that is given on page number 81, close 6.2.1. nominal section capacity kf ag an times fy. In our case an is the gross area, so 0.930 form factors, that is taken from one steel tables. 360 ub 44.7, 360 ub 44.7 has a form factor 0.930, has a gross area 5720. 360 ub 44.7, that has a gross area of 5720, and yield strength 320. 360 ub 44.7, it has yield strength 320. So 320 give us in the newtons and divided by thousands in the kilonewtons. Once you find the nominal section capacity, we can find nominal member capacity nc alpha c ns. That equation is given on the page number 83. Close 6.3.3 we have a ns value, which is the member capacity, that is alpha c times ns. We calculate alpha c 0.631, we calculate alpha c 0.61, we calculate section capacity 1720, that's given 171074. We multiply by a capacity factors, gives 967 kilonewtons. Now we should get this one larger than our loading requirement. So in our first steps we calculate the design load 1050 kilonewtons, but this capacity is less, so our trial beam is not good. So we need to we tried this we first tried this 360 ub 44.7, 360 ub 44.7, it has a gross area of 5720, which is not good, so we are going one above. 360 ub 50.7, it has a gross area of 6470, so we're going to try 360 ub 50.7, it has a gross area of 6470. Now it has a kf 9.63. For 360 ub 50.4 we have kf 0.963, and rx and ry value 360 rx is 148 and ry value 38.5. Since these values are larger than those for the 360 ub 44.7, so if we compare with these values that we try, which is 360 ub 44.7, kf, rx and ry value are larger than what we try. In that case, for 360 then we can have 5 nc, which we get it here, should be greater than 6470, which is the area of 360 ub divided by the area of that that 360 UB 44.7, that area is 5720 millimeter square, times 967 that we calculated, it's give us 1094 kilonewtons. Now we're going to compare again 1094 against this 1050. So this 1094, which is this is 1094 kilonewton, which is greater than 1050 kilonewton, that is we needed. So this 360 UB 50.7 is okay. Thank you.